Bismillahirrahmanirrahim. Now we will discuss the angular momentum. So the angular momentum. As we have already talked about the momentum, for example, we have an object which has some mass and which has some velocity. So if we have a mass and then we have a mass that's moving with some velocity, so it will have some momentum in the same direction. So momentum is represented by P. But now we are talking about the angular momentum. So the angular momentum is, for example, angular momentum depends on the reference point. For example, if we are here on the same line, then the angular momentum is 0. But if we are away from here, for example, with respect to point Q, then the angular momentum is not 0 here in this case. So the angular momentum here is, so this is the position vector. For example, position vector here at this point is here, but at position vector at this point will be something like this. So the angular momentum, so this is the position vector. So the linear, first of all, the linear momentum that we have already discussed is the mv. So anything that is moving which has some mass and some velocity will have the linear momentum. And the angular momentum, which is represented by Q here, which is represented by L, with respect to Q here. So our reference point here is Q. So that's why I wrote a Q here, which is equal to the position vector, which is this position vector, and then we have the linear momentum. So cross linear momentum. So this is a cross product. So, and we know that the linear momentum is equal to mass multiplied by velocity. So we can write this is equal to R cross mv. But m is constant. It's a scalar, and v is a vector, so we can just take this one out and then we can write the angular momentum with respect to point Q. So this point is R cross V. So we just take the mass out. So this is our angular momentum, which can be written in this way. But we know that R cross V is also equal to, so this is a cross product, so we can write in terms of the angle, for example, in terms of the sine theta. So the sine of, for example, if we extend this one here, so this will be our R sine of theta here. So we can write now, so is equal to, so we have the m here, and then we have the magnitude of R, magnitude of V, so we have the sine of theta. So this is the perpendicular, so we have the mv r sine of theta here. And now, so this is the magnitude here. So this is now the magnitude. So this is the vector. So this is, so we can write, so this is the magnitude. So L, Q, so the magnitude of the angular momentum is m r v sine of theta. So this is the magnitude here. So this is a vector. So this will give us a vector. So we don't have to write it here. So this is this will give us the vector here, because the cross product of two vectors is always a vector. But here in this case, this is since we want to know the magnitude, so for the magnitude, so we have discussed this when we were talking about the vectors. For example, this is the R sine of theta. This is our R, which is the position vector, and then we have the angular momentum. And now, since this is the, we can see here the cross product of two vector is a vector, and a vector has a direction here. So in the case of linear momentum, we know that the momentum, the linear momentum, has the same direction of the v, which is a cross product. So the cross product, the direction of the cross product is perpendicular to the first vector, which is a position vector, and then we have the it's also perpendicular to the velocity, the second vector. So, and the direction of the cross product is determined by the right hand rule. So what we do here, so we have the r cross v, so we use the r cross v, and then we can easily so in this case, so we have the r cross v, so we can write it's out of the of this board here. Now, since we know that if we change this reference point, for example, this is our reference point, as we said that if we are on this line here, then the angular momentum is 0. Why? Because then we do not have this perpendicular or this component here. This component is 0 here, so that's why we have the angular momentum. Is 0 here. But if we are on the other side here, the q, for example, is in the other side, then the angular momentum direction will be different. For example, right now it's in this direction, but if we take this reference point here, then it's outward. So this is the general definition of the angular momentum. And now we take another example for the angular momentum, which is the projectile motion. So we have in the past, previously we have already discussed this projectile motion. Projectile motion is, for example, we have an object and we throw that under the influence of gravity with some initial velocity. So it will follow this, a parabolic path. So it has some initial velocity. So this is the vi, it has some initial velocity, and then it will go like this, and we have the gravitational force. The only force that is acting on the projectile is the gravitational force. So it will have the all the time it will feel the gravitational force. That's why it will come back to the ground. So we want to know, so this is the time equals 0 when it just starts the projectile motion. So the trajectory, the first point is at point 0, means it just starts the trajectory or the motion here at time 0, and then we want to know what will be the angular momentum when the time is equal to t. The t can be, for example, 10 seconds or 10 minutes, depends on how long does it take here. So we want to know what is the angular momentum at this point when the time is 0, and we want to know what is the angular momentum when the time is not 0. So it has already covered some distance. So this is our r here. In this case, we have the r, and our reference point is here. So at the time 0, we can clearly see that the angular momentum is 0. So in this case, so we have the at time t equals 0, the angular momentum is 0. Why? Because we have this the position vector. The position vector here is 0 because we have the object is here, so the position vector is 0, although this object has some mass and it has some initial velocity. Still, it has the linear momentum is there, but the angular momentum is 0. So what we can see here at this point, we have the r, so we have the r here, and then we have the velocity and also the mass. So at time t equals t, other than the 0 here, at any point here, the angular momentum is not equal to 0. So what we see here, what we learned from this example, that the angular momentum depends on the reference point. So at this point it's 0, but it's increasing here. It's increasing here because the position vector is increasing. So we can see here that the angular momentum at this point is 0, but any other point it is not 0. So this was the general definition of the angular momentum. So and this is the general definition, but now we will take a specific example. Since we are already talking about the uniform circular motion. So the uniform circular motion, as we know, is that motion in which so for example we have the circular trajectory. So circular trajectory, for example, we have, this is for example the sun, and then we have for example the earth that is revolving around the sun. So in the circular trajectory, so we can clearly see, so this with respect to the central point, so it will have the r here, the position vector. So the position vector and the velocity is in this direction. So this is a uniform circular motion. The uniform circular motion is that motion in which the speed is constant, the speed is not changing, but the velocity is all the time changing. For example, at this moment in time, the velocity is here, but we will have the r, since the radius of the r all the time is the same. So the radius of the circle is all the time the same. So this is our velocity, and it will have some mass. So this is the velocity, and we want to know what is the angular momentum in this case. So this is our reference point, which is C. So C is for the central point. So the angular momentum, so as we know the direction, because we don't have to worry about the direction, because we can simply use the right hand rule. So the right hand rule, if it's spinning like this, the direction is in this direction, means outward. It will be perpendicular to the first vector and the second vector, which is outside this plane. And if it's spinning like this, then it will be inward here. So we know the direction. So now we want to know what will be the magnitude of this angular momentum. So the angular momentum here will be the same as we have discussed, is RC cross V. So the r is this the distance from the center, which is our reference point. So it's always the same. So, and we know that it's m r v sine of theta. So, and the sine of theta, what theta here is always 90 degrees. So here it's 90 degree, even if you're here, so it will be the velocity in this direction, and then we will have a 90 degrees. So in the uniform circular motion, we will have the angle is always 90 degrees. So sine of 90 we know is 1. So we can write m r v. So this is in the circular motion, in the uniform circular motion. So we will always have the momentum, the angular momentum will be the same. So it doesn't matter where the object is, the angular momentum will always be the same. So this is for the uniform circular motion. But generally, as we saw here, the angular momentum depends on the reference point. But here in this case, we can see here the angle is always 0, and then we have the reference point here. So this is for the uniform circular motion. So this is the uniform circular, so this is the angular momentum of the case where we have a central object. For example, we have a sun, and then we have something that's revolving around the sun. That could be, for example, a planet. We can say that it's the earth, or this is for example, the earth, and then we have the moon that's revolving. So this is the uniform circular motion. And now we want to discuss the angular momentum of a spinning disk. Disk means when this is a complete solid object. For example, we have a spinning disk. So a disk is something like this. So we have this disk here. So we want to know if it's spinning like this. If it's spinning like this, what will be the angular momentum? So we have a solid disk here. It's not like the when it's something is revolving around the central object here. So this is our center here. So it has some big mass. So we can write with the big M, and then we have this is the radius of the disk. So what we did, for example, when we were talking about the kinetic energy of the circular of the rotating objects, what we did was we take a small element of the mass. So this is the whole, the big M is the mass of the whole disk, but we will take the small m. So mi, for example, and we will first derive the angular momentum for only this small little m, for example, we have, for example, here. So you can see that we have a disk, so it has the whole mass of this disk is m, but we have, for example, a small this element, and then if we know what is the angular momentum of this for this little element, and then we will just sum all the masses, that will be the angular momentum for the spinning disk. So this is for example, this will be the tangential velocity, and it's spinning like this with omega. So this is the angular speed, and then we have this is the small element, and then we will do for the complete disk. So angular momentum for spinning disk. So for the spinning disk, so we have with the I here, for example, we have the central point is C, and then we can write the small little element mi. So this is the element mi, and then we have the radius r of I, and then we have the v of I. So we don't have to worry about the sine theta, because this is the same case. We have the 90 degrees, so the sine is always 1. So we can just talk about the magnitude of the angular momentum. As we said that for the spinning objects, this velocity, the tangential velocity, depends that how far are you from the center. For example, at the center, this tangential velocity is 0, because it's the r is 0, the radius is 0 here. But if you are moving away, the radius is increasing for the small element, and then it's getting higher. But it's not the same for all the radius, for example. But the omega is the same. For example, the point, for example, here will have the same number of rotations per second, but same is for the other point, for example, that's the same. So instead of the tangential velocity, we will use the omega, which is the same, and then which is the angular speed here. As we know that the tangential velocity is omega r, and this r, since it depends on r, for example, for the center it's 0. As we go here, it will be higher and higher and higher. So that's why we will take the omega. So we have the LC I equals m RI. So VI, so if we put this value here, we insert instead of VI here, so we will get MI R squared, because we have one R here and we have one R was already here. So RC, this is with respect to this point, so omega. And now we have the angular momentum. This is the angular momentum for this small little m. So we have the little m. So this is mi here. And now we want to know what is the angular momentum for the complete disk. So what we need to do, we just need to sum all of it. So we will take the sum, we will add all of it. So the C means C is for the center, this is our reference point, but for the disk, complete disk is equal to, since the omega, this one is omega is the constant, this is the same for all, so we don't have to add it, so it will be outside, and then it starts from I, mi RIC squared. So this is the angular momentum for this disk, but this is something that we have discussed already previously. This term here is the moment of inertia, and the moment of inertia is the same equivalent to the mass in the linear when the object is moving in the linear case. So we can write here LC disk equals IC. So this is the I is for the moment of inertia. So this is the angular momentum for the spinning object, something that is solid, and then it depends, as we know that the angular, this omega here depends on the shape of the object, and also it depends on the axis of rotation that we have already discussed. For example, if this object here, this is the disk, if it's spinning like this, so if it's spinning like this, you can see here it's spinning like this, then the moment of inertia is different, but if it's spinning like this, the moment of inertia is then different for this object here. So whenever an object is moving or spinning around the center of the mass, if it's moving around the center of the mass, then the angular momentum is the intrinsic property of that system. Then it's not changing, that as we have discussed previously. So this is called the spin angular momentum, and it is always the same no matter which reference point you take, the angular momentum will always be the same. But this is for the spin, this is called the spin angular momentum. That's why the spin angular momentum is always used when we talk about the atoms, for example. In the future lectures, when we talk about the spin of the electrons, for example, or also the atoms, we will use this spin angular momentum, which is the intrinsic property of this spinning object here, which is revolving around its center of the mass. So now, as we have already talked about the angular momentum, as we know that the linear momentum is conserved. If there is no external force that is applied on a system, then the linear momentum will be conserved. The same thing is true for the angular momentum. So we have the same law, a similar law, which is the conservation of angular momentum. So in the case of the linear momentum, if there is no force on a system, then the linear momentum is always conserved. But in the case of the angular momentum, we have the force, we have the equivalent to the force, we have a torque. So if there is no torque on a system, that means that the angular momentum will be conserved. For example, if we have a rotating object here, we have a central object here, so, and this is spinning around or revolving around this central point. If there is no torque means the ability to keep something in the, or to rotate something in circular path, but it's equivalent to the force here. So if there is no torque, on a system, then the angular momentum will always be conserved. So generally, we can write that the total momentum, the angular momentum is equal to L1 plus L2, for example, L3. So Ln equals, so this will be constant Constant means it will never change as long as there is no torque that is applied on this system. So if there is no torque, the angular momentum will be conserved. So we can also say that the angular momentum before and after will be the same. So as we have just derived, the angular momentum is equal to the moment of inertia. 1, for example, this is 1, and then we have the angular momentum. 2 will be 0. So the initial angular momentum and the final angular momentum will always be the same. So this is the definition of the angular momentum. And now, since we have already talked about all the things that are related to the angular motion or the uniform circular motion, and now we will compare the linear motion and the angular motion here. So we want to see what's the comparison between comparison between the linear and angular motion. So this is the comparison. For example, we have the linear on this side, so we have the linear and then we have the angular. So first thing is that we have a linear motion. We will have a displacement which is represented by x, for example, or a length. When we are talking about something is moving, or we want to discuss about the distances or displacement, we take a length in the unit is in terms of meters. For example, we can write this is in meters. But when we talk about the angular displacement, we have a similar one, but we take the angle. So it can be in radians or degrees, but we have the angular displacement. And then when we have a changing displacement or distance, we have the velocity. So velocity here, we have a similar one. So we have the angular speed here. So we have the speed and then we have the angular speed, which is the omega in this case. We have then when the velocity is changing, and the changing velocity is the acceleration. So we have a linear acceleration, and then this is represented by a. And then we have the angular acceleration, which is represented by alpha. We have the mass here, mass, and then in the linear case, and we have the equivalent is the moment of inertia. And then when we have a force here, force in the linear case, but in the angular case we have a torque. So these are some parallels. So we have the angular displacement, linear displacement, the angular displacement, linear velocity, we have the angular velocity, we have the linear acceleration, we have the angular acceleration, we have the mass, and then we have the moment of inertia. These two are parallels. Then we have the force, and then we have the torque for the angular motion. And same is for the equation of motions. For example, we have the equation of motions. Equation of motions. So we have the first equation of motion, which is Vf. The final velocity is equal to Vi, the initial velocity, plus at, the acceleration, multiplied by the time. So this is for the linear, and for the angular is the omega f, final angular velocity speed, and then we have the initial angular speed plus alpha t. So this is for the angular motion. And similarly we have the another. So we have the 2as. So we have this is equal to the Vf plus Vi squared. So we have the final velocity, and then we have the initial velocity. So we have the 2 alpha theta is equal to, this is plus, so So this is minus actually. This is minus here, and then we have the minus here. And similarly, we have the distance is VIT plus 1 by 2AT squared. Similarly, we have the should be theta omega I t plus 1 by 2 alpha t squared. So these are the, for example, we have the linear motion, and then we have the angular motion, and we have already talked about all these terms. When we were talking about the linear motion, so we discussed what is the linear distance or displacement, and then velocities, and then the acceleration, and then the mass, and then the forces. And similarly, we have in this chapter, we have already talked about all these things here, and then we have some parallels here, which is the equations of motion here. So we have the equations of motion for the linear motion, and then we have the angular motion.